The comparison test for series tells us that if we can compare the terms of the series, we might be able to draw some conclusions about whether or not each of them diverges or converges. However, we're not always able to make that comparison about the terms, so we're going to learn another technique that allows us to compare one series to another using limits. We're going to start out with the assumption that we have two series, one involving terms of the form a sub n and the other of the form b sub n. We're also going to assume that both of these series have positive terms. The quantity we're concerned with is the ratio of a sub n over b sub n. In particular, we want to examine the limit as n goes to infinity of that ratio a sub n over b sub n. We're going to start off with the assumption that that limit is equal to some value L, and we'll look at three cases for what the value of L tells us about our series. In our first case, we're going to be working under the assumption that L is between 0 and infinity. In other words, the limit of the ratios of the two sequences is some finite number that is non-zero. In this case, what we know is that a sub n and b sub n are growing at about the same rate. In particular, when n gets large enough, a sub n and b sub n behave as if they are multiples of one another. Our next case is when the limit of the ratio of the terms of our series is equal to 0. In this case, we know that the series a sub n is growing more slowly than the series b sub n. In our last case, when we take the limit of the ratio of the terms of our series, our limit is equal to infinity. In this case, we know that the terms in a sub n must be growing faster than our series b sub n. Let's look at what each of those cases then tells us about our series convergence. If we're in the first case, where our limit is finite and our series are growing at about the same rate, then we know that either both the a sub n and b sub n series converge or they both diverge. If we're in the case where L is equal to 0 and b sub n is growing more quickly than a sub n, that tells us that if b sub n converges, so does a sub n. Lastly, if our limit is infinite, so that our b sub n's are growing more slowly than our a sub n's, then we know if the b sub n's diverge, a sub n must as well. Let's start by examining the sum from n equals 1 to infinity of 3n over n cubed plus 5. Because of the n cubed in the bottom, we might want to compare this using a p-test. So in other words, we might want to find some way to compare this to something of the form 1 over n to the p. Since I have a cubed in the bottom but only a first degree in the top, I'm inclined to use something like 1 over n squared. So I'm going to let my a sub n term be 3n over n cubed plus 5. And I'm going to let b sub n equal 1 over n squared. And I'm going to look at now the limit as n approaches infinity of a sub n, 3n over n cubed plus 5, all over 1 over n squared. We know from algebra that dividing by 1 over n squared is the same as multiplying by n squared over 1, which turns this limit into the limit as n approaches infinity of 3n cubed over n cubed plus 5, and we know that that limit is equal to 3. So we're in our first case, where L is equal to 3, which tells us that either both diverge or both converge. But we chose a series to compare to that we know converges using our p-test. So this limit, or this series, converges by the p-test, which tells us that our original series must also converge. All right, for this last example, we're going to take a look at the series from 1 to infinity of n plus 1 over 2n plus 3. Because we have a 1 over n built into the denominator in a sense, let's go ahead and do a comparison. Let's compare our given series n plus 1 over 2n plus 3 to the series 1 over n. So we're going to evaluate the limit as n goes to infinity of n plus 1 over 2n plus 3 over 1 over n. When we do that, we multiply by n, we get n squared plus n over 2n plus 3. We can now pretty easily see that the top of that limit's growing unbounded, and so this is infinity. What does that tell us? Well, the fact that it's infinity tells us that this expression is growing faster. That's important because this series diverges. So anything that grows faster than a series that's divergent must also diverge, so we get to conclude that the sum from n equals 1 to infinity of n plus 1 over 2n plus 3 also diverges. Okay, once again, summarizing what we know. If we compare two series by taking the ratio of their terms and examine that limit as n goes to infinity, if that limit is finite, then we know that the series behave in the same way. They either both converge or they both diverge. If the limit is 0, and we know that the bottom series is converging, then the top one must as well because it is growing more slowly. Notice that in the case of the limit being 0, if the bottom one diverges, we don't know anything. In our last case, the limit is infinite, which means that our numerator is growing more quickly. Then we know if the bottom one diverges, the top one must as well. Again, in the infinite case, if the bottom converges, we don't know anything about the top.